Okay, so recording is started, and now I'm going to share the PowerPoint slide, uh, which is here. Okay, so this is uh, yeah. So we left here in the last class. So we were talking about the flux quantization. So you can see that in a superconducting ring, the flux is quantized, just as charge is quantized quantity. In an electron orbit, the angular momentum is a quantized thing. The energy is quantized in quantum mechanics. Here in superconducting ring, the flux is also quantized, that we proved in the last class. So now let me go further. Now this is a phenomena associated with the superconductors. There is something called Josephson tunneling. So what is Josephson tunneling? That you have an insulator. You see where my cursor is. This is an insulator, and there are two superconductors on both sides. So this is connected with the superconductors, and this insulator is very thin, so that the current can tunnel across from here to here. You already know the tunnel phenomena in quantum mechanics, the tunneling phenomena, so that the electron can tunnel from one side to the another, though there is a insulating barrier here. But this barrier has to be very, very thin. So only then this tunneling can take place. So first, I will talk on Josephson effect, and there are two kinds of this. This is DC Josephson effect and AC Josephson effect. And then associated with, there is a microscopic long-range quantum interference. This has a very interesting application in nowadays when we work with the nanomaterial. So what is this uh, DC Josephson effect? So DC Josephson effect is, interestingly, that if you uh, close this circuit of superconductors, having two superconductors and insulator in between, and you don't apply any voltage, even then what happens, there is a current flow in the circuit. There is a DC current flow in the circuit. Similarly, if you apply a DC voltage across this junction of superconductors through insulator, then also there is a current, but this time the current is AC current. Though your source is DC, you have just applied battery, but the current which flows through the superconductor is AC AC current. So that's called AC Josephson effect. So we will understand its origin quantum mechanically and explain this, how this actually takes place. So this is first we see this DC Josephson effect. So now here you can see that in this diagram, um, here if it was just a ohmic system, where V is proportional to I, on x-axis you have V, on y-axis you are plotted as I. So this would be just an ohmic system. This would come as a straight line if you have a V is proportional to I. But here you see that this Vc is some critical value where it is no more superconductor. So up to this critical value, you can see that there is a current flow, though you have not applied any voltage here. So this, you can see, it's a step measured over here, and this is interesting that it can flow in this direction and in this direction as well, but you have not applied any voltage. It's only after you apply voltage, it's a normal system and it behaves like a ohmic system where V is proportional to I. So in this region, the current into the system flows without any application of voltage. That's a DC Josephson effect, and we will explain this using the equations of quantum mechanics. Now, let's say this is how we have made this system, and the insulator is there in between. So we write a wave function of a Cooper pair this side and on this side. So this is N1 half e raised to the power minus I theta 1. This we defined already, the wave function for the Cooper pair. It has amplitude and phase factor, amplitude and phase factor. Here the subscript 1 and 2 designate whether Cooper pair is on the left side or right side. If it is Cooper pair is in this region, you say it is 1. If the Cooper pair another side, you say it as a 2. Okay, so now you can see that here you see that dim kind of dotted line is a kind of wave. You know, Cooper pair, as you know, this can also be a wave, just as in any particle is a wave, just like electron is a wave. So you can see that when this would be there, this phase at theta 1 would be different from the phase at theta 2 here. So it's a phase change of this wave is represented in this dotted line. Now we have to write time-dependent Schrodinger equation. Let's write this, and we know that this is what time-dependent Schrodinger equation is: IH cross d psi upon dt is equal to h psi. Okay, so this is Hamiltonian, and this is Hamiltonian operator, and so there is no potential energy associated because we do not have applied any external voltage to it. So this is how we write that IH cross d psi 1 dt is equal to h cross t psi 2. That's how we write this equation. This equation, this h cross t is a energy actually, or you can say h cross omega if you know that if you apply Hamiltonian operator, you get h cross omega. So this t here is that omega, which you already know, but here we are calling it as a um, uh, uh, T has a dimension of rate of frequency. It is a measure of leakage of psi 1 into psi 2 and psi 2 into psi 1. So this is transfer rate. I mean, this boson, or you can say this Cooper pair, is having a rate of transfer from one side to the another. So this represents rate of transfer basically. And this together has a dimension of energy. So we can write here that uh, or the measure of leakage that this Cooper pair has transferred from region 1 to 2, or from region 2 to region 1 and region 1 to region 2. So that's how these equations are symmetric because this again has a dimension of energy. So instead of calling it a frequency, here we are calling it a measure of leakage because one particle, which we say Cooper pair, is leaking from one region to the another. That is why there is a current. Otherwise, there will not be any current. So this is a measured thing. You know, from this measured thing, we are using the time-dependent equations. We are writing this initial Hamiltonian equations. Now, dimensionally, these equations are correct, and they represent transfer from one region to the another. Okay. Now, having this written this equation in this way, now psi 1 you already know this represent n1 because Cooper pair or is the density particle density of Cooper pair in region 1 and 1, and here it is n2. This is in region 2. So this is a phase factor at the boundary in region 2 and the phase factor in at boundary 1. Now to satisfy the equation 1, because in equation there is a time derivative of psi 1 and psi 2. So let's have a time derivation of these equations. So these are normal time derivations. You can see that if you do the derivation of this, you get half here and minus half there, and then you had dn1 upon dt e raised to the power I theta, like this. So this is differentiation by parts. That's what you get, and minus I t2 psi. So this is from this equation. If you see this first part of equation, iota comes because this, if this is iota here, I take this minus iota there. So basically this equation which you see here is nothing but comes from the this first set of equation 1. Equation 1 में जो पहला set है उससे ये आ रही है. ऐसे ही ये दूसरी आ रही है। मैं जस्ट 1 मिनट के लिए रुकता हूँ, सो दैट अगर आपके पास कॉपी पेन है तो आप इसको देख सकते हैं करके, एंड यू कैन बी you can verify it. I hope so. Not in a hurry to go from here. You can understand how this uh, derivation of this is giving this equation using first, and then derivation of this equation is giving you that one. Okay. So I think is clear to you now. You are convinced, I guess. And now here it is written on further solving above equation yield. So how we going to further solve these equations? That here you can see that dn1 upon dt is there. Here it is there, and this 1 upon 2 is there. So we have to multiply some factor here in this equation and some factor in this equation here, and so here you need to multiply n1 n1 raised to the power half e raised to the power minus I theta 1. So if you do that, this term will disappear, because then that term will have just power of the opposite sign. Okay, so you can see that none of it exists here. And I n theta 1, theta 2. So this is psi 1 here. Psi 1 is n half, and you are already multiplying by n raised to the power half. So there will be n1 here. I is already there. And you are multiplying by e raised to the power minus I theta 1, and because of psi you have I theta 1, so I theta 1 will cancel, so you will have this I n1 del theta dt. So on the right hand side, so this would be t, and psi 2 is there, n half e raised to the power I theta 2, and you are multiplying with n1 half, so you have n1 half n2 raised to the power half, that is why, and e raised to the power minus theta 1 would be there. So I theta 2 is due to psi 2, and I minus I theta 1 is due to multiplication. So you have here I delta, which is theta 2 minus theta 1. And similarly this. Here you also again do the same thing, that you multiply this entire equation by n2 raised to the power half, e raised to the power minus I theta 2, that's you get. So just I'm waiting for 2 minutes for your verification of these equations. And once you are satisfied, you can just raise your hand, or can tell me somehow that okay, you have done it. Maybe if you one or two of you raise your hand, then I will understand, okay, you understood this. Okay, so some of you have raised your hands, 4 participants. Okay, good. Okay, now no need. I hope it's easy. You can do it later on also, because I will share my slides with you. When this is over, I will give you the slides. So I6, this is 7 raise hands, and that means you have many of you, 8 participants are raising hand. Okay, good. Okay, now no need. That's fine. I'm just going forward. 9 raise. Okay, good. Yeah, good, good. So fine. So let me go forward. Okay. So now come to this slide. Fine. Okay, now you can lower your hand, and that's fine. Now let's come to this slide, and um, now from the last equations, now you have to what you need to do is do the real and imaginary part separation of imaginary and real part from this last 2 equations. Okay, so you see that here you have iota here in this equation, and iota, so this is the real part, this is imaginary part, and this is because I delta theta is there, so you will have cos theta plus I sin theta, so you will have real and imaginary part on both sides. Once you separate them, this is what you get. So dn1 upon dt is 2t n1 n2 half sine delta dn2 upon minus 2t, this one, and the imaginary part. This lower side, this is the imaginary part, separation of imaginary parts of two equations, and this is the real part. Okay, so not very um, something intricate calculation, simple just separation of this real and imaginary parts, and you can do that. Um, so just see if this is correct, and I will just now make assumption here that n1 is equal to n2. So the density of superconductors on side 1 and side 2 are equal, because we assume that these two superconductors on both sides of junctions are identical. So that is an assumption. So then n1 is almost equal to n2. That's what we take here. So if we do that, n1 and n2, so you do here n1 n2, or you put it n, so this is n square and n raised to the power half to 2tn minus 2tn. So that is how you have this dn2 dt minus dn1 upon dt. This is what you get from there. And if you put n1 is equal to n2, this is 1, so minus t cos delta and minus t cos delta, they become equal. So that's why theta 2 minus theta 1 is equal to 0. Okay, so this is constant. That's how we get it. So this is also telling us, this is a very interesting equation where my cursor is moving. It tells us that rate of change of uh, particles, Cooper pairs, the particle is Cooper pair is here. The rate of change of particles in region 2, or increase, because there's a positive sign, it's a rate of increase, is equal to the rate of decrease of Cooper pair in particle 1. So it is clear, because it's conservation of Cooper pairs. From one side, the Cooper pairs are going and entering into the another region. So this is telling us the conservation. So this is very good thing we have got. And so now, current density. So just from the definition of the current density, this is what is employed here: charge and rate of change of particle density, charge multiplied by rate of change of particle density. So that's current density. So Q is 2E, because Cooper pair has a charge of 2E, dN2 upon dt. So we do dN2 upon dt. So minus 2t is there, and so n1 n2 half sine delta. This we take as 0. Okay, so this is a sign. Basically you can take it negative also, it doesn't matter, because it only indicates the direction of currents here. Okay, so this is how you get J is equal to J naught साइन, इसको हमने J naught बोल दिया, ये जो क्वांटिटी है यहाँ इसको हम J naught कह रहे हैं, sin theta 2 minus theta 1. Now this is an interesting equation. This is telling us that if you have a definite phase difference of theta 2 minus theta 1, so sin theta having some value, there will be a definite current density. Okay, so J naught is some factors, charge, tunneling probability, and density, or all sorts of things, they are constant. Now current density will be 0 if theta 2 if this there is no phase difference. Okay, so here, from here, delta theta 2 minus delta theta 1 is coming out to be 0. So that means theta 2 minus theta 1 is constant, and that is delta. So this is a constant. If theta 1 is equal to theta 2 somehow, then there is no current, because sin theta will be 0. This is with sin 0, and it will tell us there is no current. Now this is having a definite constant value, because if you just see I'm just taking you back here. If you see here at the boundary, this theta 1, if you see this dotted wave, this is not very sharp, but it's drawn with a very mild color, this a wave. Now you see you have theta1 phase here, and the phase at the boundary of other region is theta2. So there is always a difference between theta1 and theta2. So this difference will disappear if this junction become very thin and completely disappear. Then this theta1 and theta2 is equal to 0. So तब जो Josephson junction होगा ही नहीं. So there is no Josephson junction. So as long as we have this Josephson junction, there will always be difference between theta1 and theta2. Definite difference will be there. Difference will be there. So when we have a definite difference between this theta2 and theta1, there will definitely be a current. So this is an explanation actually. जो जोसेफसन ने मेजर किया था, उन्होंने देखा कि in such a junction you still have a current flow in the system though you do not apply any voltage. So why this is? So we have a quantum mechanical explanation of it. We can write a Schrodinger equation, time dependent Schrodinger equation, and from where we can derive this Josephson equation. So this is now I will come to this AC Josephson effect. So that was a DC Josephson effect. Now these equations will change slightly. So now you see, as it is written, when a DC voltage is applied across the junction, we get AC current through the junction. We can say that pair 2E, this is a Cooper pair, has a potential energy minus E on one side and plus E on the other side. The time dependent equation of motion becomes. तो देखिए ये जो 2E एनर्जी है, पोटेंशियल एनर्जी है, इसको आप ये कह सकते हैं कि एक साइड 0 ले सकते हैं और एक साइड 2E ले सकते हैं. So that is also a way. But just to keep the equation symmetric, one side we have taken this potential energy to be minus EV, another side to be plus EV. इनका difference अगर आप देखेंगे तो 2EV ही आएगा यहाँ पे. Okay, so आपने एक voltage का difference लगाया है. So naturally, now when you would like to write an equation, here in the Hamiltonian, this potential energy term will also come. So if you can write it on the other side here, in this side you can see that plus EV term is there, and in this side if you write, it would be minus EV. It is all about that how you would like to, if you want all your psi 2 on one side, you can take this and write it on this side. You can take your psi 1 on this side. That's how, if this equation looks good to you. Earlier we did not have a potential energy. Now there is a potential energy also, which is also playing its role in the motion of the Cooper pair. So that is what, this is a Hamiltonian operator, and then you have plus potential energy that will determine the rate of transfer or rate of leakage into the another region. Similarly here. So that's how we made our equations symmetric. Rest of the things are same as you did. Psi1 is n1 raised to the power half ei theta 1, n2 raised to the power half I theta 2 in the above equation. It's only the initial equations, that's only you have to understand how to write these initial equations. If you write that, the rest is a simple derivation. You can do that. Now, once again, I'm not doing the same thing again here, which we did already, separating real and imaginary parts. तो हमने यहाँ पे ये जो इक्वेशन है, इसमें d psi 1 upon dt ये करना पड़ेगा, psi 2 की वैल्यू यहाँ रखनी पड़ेगी, psi 1 की वैल्यू यहाँ रखनी पड़ेगी, all this, and then again you will get some equations where you will have real and imaginary parts. So this is what the your real part is same as the last. You can see that real part has not changed. It is coming out to be exactly the same as you saw in the last time. In the imaginary part, due to this EV, you have this EV upon H cross factor is coming here. When you solve these equations, so that would be a kind of assignment for you to solve. It is already solved here. Just have to put in and do it. Okay, so this imaginary parts is getting changed here because of this introduction of this potentials in this equations. Now, same that density in the both regions are identical or almost identical. So here, this from the real part, this is again the same thing which is coming, that the rate of change of particle density or rate of increase of particle density in region 2 is equal to the rate of decrease of particle density in region 1. So this is again a conservation law of charge or mass, whatever you would like to say. And here uh, your d upon dt d theta 2 minus T1 is coming out to be minus EV upon H cross. This last time it was coming out to be 0. D theta 2 minus d theta 1, it was 0. You can see it's 0 here. This time it is coming out to be minus 2 EV upon H cross. Sorry, I think this delta is equal to constant is probably not correct, because I just copied from the last equations and it remained here. So this is what is constant here. Okay, so now when you integrate this equation, so delta depends on t here. Now delta has a t dependence here when you integrate this equation, and that's what you get on integration. 2ev h cross into t, and that's what I call delta t and delta 0, because at t is equal to 0, this delta is equal to 0. So this is a constant of integration, and that's what you get. इस equation को integrate करने पे ये मिलेगा आपको with the initial condition. Now you can see here current density is J is equal to J naught sine delta 0 minus 2 EV upon H cross. So now it depends on T. You can see that though you have applied some DC voltage which is time independent, क्योंकि आपने जब DC अप्लाई किया तो DC तो कांस्टेंट है, टाइम पे डिपेंड करता ही नहीं है, एक सिंपली एक वोल्टेज है. Now T is coming here as the time is running, as from 0 to some point, this sign factor will keep on changing as a function of time. So if it is changing as a function of time, means your current will be having a sinusoidal behavior. So if a current is having a sinusoidal behavior, it is an AC current. Or if you compare this entire thing with the omega, you call it omega. Okay, the delta 0, you can call it 0. If you fix your phase of wave in such a way, you can set this equal to 0. You want to start at such a point. So then that's what you have. And if I say 2e v upon h cross as omega, so this is sine omega t. So this is the frequency. This is the frequency of this AC with which this is the frequency of the AC current which we get after applying the DC voltage. DC voltage अप्लाई करने के बाद जो आपको यहाँ AC करंट मिलता है, ये उसकी फ्रीक्वेंसी है. तो a DC voltage of 1 microvolt you have, यहाँ पे हम कैलकुलेट कर सकते हैं 1 माइक्रोन वोल्ट. ये देखिए सारे जो कांस्टेंट है, H क्रॉस की भी वैल्यू पता है हमें, E की भी पता है, तो यहाँ पे 1 माइक्रोवोल्ट वैल्यू रखो और देखो कितनी आती है फ्रीक्वेंसी. दैट केम आउट टू बी 483.6 मेगाहर्ट्ज. तो ये बहुत बड़ी फ्रीक्वेंसी है. जब हम AC करंट कह रहे हैं तो ध्यान रखें कि जिस हम AC करंट जो हम जानते हैं, जिससे परिचित हैं, वो 50 हर्ट्ज की होती है, जो हम अप्लायंसेस में यूज करते हैं. ये मेगाहर्ट्ज में है, 483 मेगाहर्ट्ज, समथिंग अराउंड गीगाहर्ट्ज के करीब आ रही है. मतलब फ्रीक्वेंसी है बट वेरी हाई फ्रीक्वेंसी है इसके अंदर. ओके, सो this is what this is the AC Josephson effect. Okay, now this is the last chapter in this one. This is called microscopic quantum interference. Microscopic quantum interference. अब इसमें जो डिवाइस है वो देखो आप, जो डिवाइस है, it is of this kind. First of all, we have to understand that what we are willing to see is that there are two Josephson junctions. ये एक Josephson junction यहाँ है, दूसरा Josephson junction यहाँ है. हमने दो Josephson junction लगाए हैं और मैग्नेटिक फील्ड लगाया है. ये जो B है अंदर दिख रहा है, ये is perpendicular to that there is a magnetic field. And now you have a J total current flowing through this, and then it is diverting through these channels, and then this is coming back, and there it is again interfering. तो इंटरफेरेंस करने के लिए आप हमेशा देखते हैं, चाहे वो लाइट का इंटरफेरेंस हो या यहाँ करंट का इंटरफेरेंस हो, उसमें आपको दो signal chahiye. Light, maybe you need a double slit experiment so that you have light coming from one slit, another slit, and they interfere at some point. Here, you have a current coming from one junction and current coming from another junction, and when they meet in phase, they produce constructive interference, means larger current, or when they meet opposite in phase, they produce destructive interference. This is the interference of current basically. This is how this system is basically designed. Now let's see what it is saying, that we consider two Josephson junctions in parallel as shown in the figure. No voltage is applied. Okay. Let the phase difference between points 1 and 2 be delta A and delta B for junctions A and B. In absence of magnetic field, these two phases must be equal. What it is saying that, when you have this two two currents taking two different paths, when they meet here, they will be in a same phase if there is no magnetic field. So you have taken and just an identical circuit, identical Josephson junction on both sides. So current bifurcates here, and when they meet, they will meet in a same phase. No difference unless you apply a magnetic field. Because in a closed circuit, you also know in the superconductors that there is a quantized magnetic flux. Because this is a superconducting ring. If you would like to see it like that, a superconducting ring ban gaya. Okay, so let the magnetic field be applied normal to the parallel circuit as shown in the figure. The phase difference of the two path is given by, अब ये phase difference जो magnetic field की वजह से आ रहा है, वो delta B minus delta A is 2E upon H cross C phi, और ये जो टोटल फेज डिफरेंस है यहाँ पे, इस फेज डिफरेंस को आप इस तरह से भी ऐड कर सकते हैं, डेल्टा नॉट प्लस हाफ ऑफ इट एंड डेल्टा नॉट माइनस हाफ ऑफ इट. इनको आप डिफरेंशिएट, इनको आप डेल्टा बी माइनस डेल्टा वन करेंगे. सो दैट्स व्हाट यू विल गेट द फेज डिफरेंस बिटवीन द टू जोसेफ्सन जंक्शंस. वी नो दैट वो एक मिनिमम जो फ्लक्सॉइड है, जो मिनिमम फ्लक्स है, उसका एक integral multiple hota hai. So this is why we are going to get this. Now let us now, because in interference you superpose this current, so J is equal to JA plus JB, or sine delta E H cross C plus sine delta minus E H cross by phi. So when you do this, you see that this is simply the formula from the sine A plus B plus sine A minus B. So that comes about 2 sine A cos B. So if you do this, if you do that, that's what you get. J is equal to 2J naught sine theta naught cos E phi upon H cross C, and the flux is defined as B dot delta sigma here. And what is the interference term here? You see that J naught, this delta naught here is a constant thing. So this sine delta naught, it will be constant. J naught is constant. E phi H cross C. So if you change the magnetic flux, so this is phi. If you change the magnetic flux here, so then you will have a change in current. So basically, you go on changing in the magnetic flux, you go on increasing, and you will have change in your J, and that change will be sinusoidal because it's a cost function. अब psi को एक वैल्यू से दूसरी वैल्यू तक चेंज कर दे जाएंगे, बट इस फंक्शन की वैल्यू रिपीट होगी क्योंकि कॉस की वैल्यू -1 और +1 के बीच ऑसिलेट करती है. चाहे आप मैग्नेटिक फील्ड को एक ही डायरेक्शन में इंक्रीज करते चले जाएं, it will have an oscillation like this. So this is what is an interference. So basically here it is shown that if you initially there is no magnetic field here, if you apply a magnetic field and keep on changing this magnetic field, what you have is this kind of uh, interference. And from this interference term, the maxima, minima, maxima, minima, maxima, minima, you can get back this magnetic field. Okay, so this you can get back this value of phi here. From phi you can get back the magnetic field. इसका एप्लीकेशन कहाँ है, आप इसको समझेंगे कि जब हमारे पास बहुत छोटे सिस्टम है जिनका मैग्नेटिक फील्ड मेजर करना, जिनका मैग्नेटिक इंडक्शन मेजर करना बहुत डिफिकल्ट है. जस्ट लाइक यू हैव नैनो मटेरियल्स, यू हैव फ्यू एटम्स, few hundreds of atoms there. The material is so small that the sensitivity of any material will not remain over there. You know, you need, there is a question of instrumental sensitivity when the material becomes so small. How small magnetic field you can measure? So here you can see that a very small, even this technique is very sensitive, that even a milligauss magnetic field you have, it produces this interference, and you can measure. And based on this principle, this device is made, which is called SWAN, superconducting quantum interference device, or SQUID इसको हम कहते हैं. And this is one of the modern device available in the laboratories where people study magnetic properties of nanomaterials. So in the research laboratories, this SQUID is one of the very modern technique which is available in India in many places, like if you go to Delhi, Mumbai, IISc Bangalore, and all these places, this SQUID is there. In Delhi also there, I think in Chandigarh also there at some place. So what is the purpose of this? This measuring the magnetism at low temperature, measurement of a small magnetic field. Now you can see how small you can measure, 10 raised to the power minus 18 Tesla. This is extremely small magnetic field which you can measure just from the very small samples. So this is very useful in nanomaterials where specimen is very small quantity, and so that magnetism by other techniques, by just like vibrating magnetometers are available to measure the magnetic properties of some bulk substances. But when you have a very small amount of material, it is extremely impossible. And this provides us, this macroscopic quantum interference provides us the way how one can basically measure this. So this is, you can say, very now this equation, you think how it is coming, because this I have already told you in the when I told you about the flux quantization. You must be thinking where from this equation is coming. So you can just go back to the flux quantization and uh, uh, check this equation. So this theta 2 minus theta 1, which is coming out to be q upon h cross c into 5. So this derivation we have already done previously. Okay, so this is what I have used here. So whatever is there in your syllabus, I have completed now this chapter of superconductivity, and the kind of questions which you will face. You see, first of all, I don't know in this situation what will happen to your examination, whether you will be having any examination or not, I don't know. Because you see, the situation is going like this, and suppose you have an examination, what kind of it will be? Will it be just based on internal assessment कि भाई इनका internal assessment कर लो, उसी के बेस पे हो जाएगा? तो बहुत सारी possibility चल रही हैं जिसका हमें अभी नहीं पता एक्चुअली ये क्या होगा इस सेंस. ये तुम लोगों को उसी तरह से प्रमोट किया जाएगा या एग्जाम लिए जाएंगे या जो भी है. मान लिया अगर ऐसे ही होता है तो, लेकिन जो भरपाई है जो तुम लर्निंग इस सेमेस्टर में करते हो उसकी तो नहीं हो पाएगी. सो दैट इज द मोटिवेशन कि जिससे कि आप मान लिया चलो पास भी हो जाएं, या इंटरनल असेसमेंट हो, या जैसा भी हो, या एग्जाम हो, वो हमें अभी नहीं पता. तो यू कैन लर्न दिस. सो सुपर कंडक्टिविटी का जो सिलेबस है आपका, जो एमएससी से रिलेटेड है, इस चैप्टर से ये टॉपिक खत्म हो गया. इसके बाद मैं आपको कल और परसों नहीं मीटिंग रखूंगा. आई जस्ट गिव यू अ 2 day गैप फॉर दिस. In the meantime, you can study this superconductivity, have your questions prepared and send back to me in writing file. So I can just one by one take up your question and answer. And I will also give you a set of questions. Suppose there is an examination, so you can be prepared for it in this situation. Okay, so if anybody has to say anything, I would say now they raise their hand and I will go to them one by one and ask them what they have to say. किसी को कुछ कहना है तो वो अपना हाथ अभी खड़ा करें, कुछ भी पूछें आप. आज का ये चैप्टर है, ये हमारा हो गया. So we have 37 participants, and as we know, there are a lot of speculations right now, and we do not know about it. कि जो examination होंगे वो किस तरह से होंगे.